So, good afternoon. So, today I will start we are going to compute a generating set in 2 points in a certain Kummer extension. So, we'll give an example how we can do that. Yesterday, we saw that if you know a generating set in 2 points, you can, from that, recover the Weierstrass semigroup in 2 points. Okay, so we will start doing this. So we'll compute. So, well, this is going to be an example. So we are going to consider a Kummer extension. So just a total, right? So we are going to consider like this. So we take y to the m equal to fx. F is a polynomial. Okay, so it's just it's a separable polynomial. And the polynomial has degree r. And we ask that, well, the degree of f and m, they are coprime. So we have f is separable. And we ask that the GCD between this guy and this guy is 1. Okay? Yesterday, we worked with the Mitchell function field that's like this. So actually, this is a particular case on this one because the GCD between Q plus 1 and Q is always 1. So basically, the computations we did yesterday for the Mitchell function field, they will be the same for the function field of this algebraic curve. Okay, they will be not the same, but very similar. So actually, we know again here the divisor of the function x here and the divisor of the function y in this function field. So as yesterday, we just considered them. So f is going to be we do f cubed, right? And you consider this. Oh, this polynomial y to the m minus f is irreducible since f is separable. Okay, so we know that this extension has degree n. And just like yesterday, if you look to the pole of y here, okay, then you know that this is going to be totally ramified. So you have just one placeholder with ramification index equal to m. And also, if you take any root of f, so I'm going to suppose that the roots are in f cubed. So let's say alpha I is in f cubed. Okay, we are over finite fields. So this is never asking too much. Since, okay, you have R roots, so for sure, your R roots should all then live in some finite field. So just take the largest one, they all live there. And you consider your curve here. Okay? So what we know is that if you take alpha, so for each alpha I will associate a place here that I will call Pi. So this place is just P associated to a reducible polynomial x minus alpha I. And they are roots of this guy. And just as yesterday, if you remember, we saw that this place, they were also totally ramified. So call it Q index I over here. So we also have ramification index here equal to m. Okay, so this is going to happen for I from 1 to r. So what we are going to do here, we are going to compute the generating set for the places Q infinite, Q1. Okay, so who's this guy? So yesterday we saw how could you compute that. At first, we need to know the gaps at this place, Q infinity, and also the gaps at Q1. So for Q infinity, just like yesterday, we have that the Weierstrass semigroup at the infinite is just generated. Okay, before this. Well, we want to compute this, and just like yesterday, what we have is the divisor of these functions in F. Okay, so this function up here has just one pole at Q infinity, just 1, 0, this guy. So this is just M Qi minus M Q infinity, and the divisor of Y on F is the sum from I equal to 1 to R of the Qi's minus R Q infinity. So we have this. Then we want to compute this generating sets. Okay. So we have that the Weierstrass semigroup at Q infinite is generated by M and R. Okay, so we did all this for this curve, but if you look here to these divisors, you see that R is in the semigroup generated by this, M is in the semigroup of Q infinity too. So we know that this semigroup is contained in this one. And now we have that the curve here, this curve has genus G equal to M minus 1, R minus 1 over 2. And it happens that the genus of the curve is equal to the genus of the semigroup generated by this one. So they're equal. So the argument is exactly the same as yesterday. And well, we also have. So this you can find proved somewhere. No, you can find in a paper. Like we know the Weierstrass semigroup at the point Q1. Okay, actually, it could be key index I. Doesn't matter which one you take. So for this guy, we know that this is just N minus M times J minus 1 plus I, such that I is between 1 and M minus 1 minus M over R. So this is just the 4. And J is between 1 and R minus 1 minus this. Okay. So you see, this Weierstrass semigroup at this guy is natural numbers less these guys. So it means that we are saying that actually this is the gap set at Q1. Yeah? So my claim is that this guy is equal to this set. Minus MJ. So you see in the second coordinate, I just put the gap set here. And we will see that these are also gaps at the infinite. And for I and j, as before. So we have one I here. And for each I, j varies from r minus 1 minus it's r times I over n. Okay. So yesterday we saw, how can you prove that they are equal? Well, let's say that this guy, we call this guy gamma prime. So we want to prove that gamma prime is equal to gamma. So we have to do three things. We need to prove. So at first, we are going to prove that, notice that gamma prime is contained on GQ infinite times GQ1. Okay, well, yeah, the second part is just by definition. Okay, this is the gaps. So it's just by definition that the second coordinate is a gap here. Oh, sorry, I put P, but it's Q. Q1. Okay. And what about the first one? Well, if you look to these numbers, yeah, what is the semigroup generated by M and R? You should have here like MX plus RY, and X and Y should be larger than 0. Yeah, but if you just put M like here, you can see you have a multiple of R like that's negative. And if you put R, you can see also that you have something negative. So yeah, these guys are not in the Weierstrass semigroup at infinity. They are gaps here. So this is okay. This part is okay. Now what we need to prove also, we are going to prove, this is usually the harder part. You have to prove that this is contained in the Weierstrass semigroup and these 2 points. So, yeah, for doing this, what you have to do? Well, you have to find a function on your function field such that the pole divisor of your function will be this guy. Will have such that the pole divisor of function will have order this at Q infinite and order like this at Q1 and no other poles. Okay, so I'll give you the function. So for this, let z equal to this function, y to the m plus 1, m minus I. Now we take fx, the product of all the roots, to the power minus m minus I, times the first one, we are at q1, to the power minus j. Okay. And we compute now the divisor of zeta. So we know to do these things because we have all the divisors. So this should be the divisor of this plus this divisor plus this divisor. But this divisor is just m plus 1, m minus I, times the divisor of y. And we know the divisor of y, it's here. So the divisor of y is just the sum from 1 to r, qi minus r q infinite. Okay? So this is this one. Now we need to add this guy. So this should be the divisor of this function. Okay, so I should put this down. It's minus m minus I, the divisor of f. But who is f? Well, f is the product of all the roots. So what's the divisor of f? Is the sum of these divisors. And I have each divisor here. Okay, so this should be this times the sum of this guy. Okay, so m this guy, and now for each q index I have r times q infinity. So actually we have here m, okay, like this. Okay, so each one is the divisor of x minus y. And we still need to add this guy, so it should be minus j, the divisor of the first one. That is just m q1 minus m q infinite. So, well, well, let's see what we get here. So what we get with this guy? So we have this, m plus 1, m minus I, minus this, that's here, and well, and this everything. Okay, what we get with infinity? So with infinity we have m plus 1, m minus I. So this guy times minus r, so you have like minus r here, this guy. And now we have this, minus with minus, so we have m, but we have r times, so r m minus 1. And we still have this guy, plus jm q infinite. Okay, and now we have this guy alone, q1. So you have to do the computations. I will not do all them here. So you finish the computations. What we get is, so for this guy, okay, this is here, it's easy to see now, m plus 1 this, so I have m times this. So I have m minus times the sum. Okay, so I'll just let the y equal to 1 out to put with that guy. So equal to 2 to r. And so actually this is m times this. Then for q1, I have this guy that is minus m times j minus 1. That's what I want. And at the infinity, we have minus r m minus I minus jm q infinite. Okay. And these are exactly what we wanted there. Okay, so this is what we have here, and this is what we have here. And these guys, they are for sure positive. Okay, so this function has only poles in these two places with the order we wanted. Okay. So we found this set contained in the intersection So, what is missing? To know that is everything, you should just to know how many elements it has. Remember that the generating set has G elements. Why? Yeah, because it's connected with the graph of that bijection between this set and this set. Okay? So for the second part, so now it is enough to show okay. So we just compute this. So gamma prime is this guy. So for each I, we have a J varying here. So we have the sum for I from 1 to M minus 1 minus the floor of M over R minus 1 minus Ri over M. Okay. Also, well, this part doesn't depend on I, so you just have M minus 1 minus this times R minus 1. And now you have minus the sum from I to M minus 1 of these guys. So yeah, usually, well, we don't know to compute this. But we know to compute this floor if I just add from 1 to M minus 1. So this is what we'll do. We'll just write this like this one. Huh? So this part I can just write as the sum minus 1 of this. So I do. Okay, so I'm just doing, well, minus, plus, and now I do the other part. So it should be the sum from I equal to M minus, I take off this part, and I do to M minus 1. Yeah. Okay. So this can be written as this part, huh? Because I just do, yeah, the sum of everything should be this sum plus this sum. Okay, so this, and now now it gets easier because this part we know. So this is just M minus 1, R minus 1 over 2. And what can we say about the second part? Okay, I forgot here. I have this, I over M. Well, for this part, let's check what we can do. Okay, so we have I varying from M minus M over R till here. So if I do Ri over M, so this should be, I just multiply by R over M, so this should be R minus R over M. And here it should be R over M, so I just have R minus R over M, M over R. Okay, and now you just take floors. So when you take floors here, We are lucky because, well, the floor here will be just R minus this floor. Okay, so this floor is going to be the floor of this guy is -1, so this is -1. And yeah, you can convince yourself that this is the same. The floor of this guy is just -1. Okay? So for this part, actually, you are adding the same thing all the time. Huh? This is just R -1. So what we get with this sum is just M -1 minus M over R. This times R -1. This part was, was minus over 2. And now, well, you are adding the same number this times. So you have -1, M -1, minus M minus this. Okay. So you see you have a lot of R -1 over there. So you can see that you can cancel this guy like M -1 with M -1 here. And minus okay, so R -1, M -1. Okay, so what? It's better if you just do all this. What is this? This is actually just M -1 minus M -1. So actually, this is just this. Yeah, it's better like this. And so you have So now these guys go out with this part, so it disappears, and so you just get what you wanted: M -1, R -1 minus half of it. Okay. And this is just what we wanted, the genus. So, well, we found a set that's contained on this intersection of size G. So as we saw yesterday, it has to be the generating set. So for Kummer extensions and two totally ramified places, I always know the generating set, okay? So this is an example. And now I will move on to pure gaps. Okay? So pure gaps can be used to improve the minimum distance of certain codes. Okay? So let's start this part. So now we go to pure gaps in 2 points. So this concept was introduced by Roma and Kin. Okay, so it's an important subset of the set of gaps. So we are going to call them pure gaps. So these are the pairs. So what we want now is that we want that the dimension of this guy is equal to the dimension. If I just take one here, we want this, and we want that the dimension, if I take one here, it's the same too. So, okay. So these are called the pure gaps. So remember from yesterday, we had that being a gap, it means that you had this equal or this equal. Now you wanted both equal. Okay, so for sure, this is a subset of the gaps at the 2 points. And yesterday we had characterized the set of gaps. Okay, what does it mean? So now look, we have that this dimension has to be equal to this and also to this one, and we'll show that this is equivalent to say that the dimension of this guy is equal to the dimension if I put a minus 1 here and also b minus 1 here. Okay, so for doing that, I will do at first a lemma. So we begin with something that we need. And it says the following. You take divisors A, B, and E, divisors in F, such that the divisor A is smaller than B, and E is larger than 0. Okay. And we suppose also that the support, you see, if you do B minus A, this is also effective divisor, it's a positive divisor. So you want that the support of the difference of B minus A and I, they have nothing in common, it's empty. And then what you have is like, then the following function, we are going to consider this function. So we have A is smaller than B. So we can do this space over this. Okay. We have this Riemann space contained here. Also, since A is smaller than B, A plus E is smaller than B plus E. So I can also consider this. Okay, so, and we have a function from here. Okay, so so we have this, and we are going to show that, well, this is like this is well defined, and actually this is injective function. So this is a function, okay, defined, this is a linear function. This is a function between vector spaces. So this is injective. Oh, if it's in, okay, this is, and then we are going to use this next. So let's prove this. So just consider first a certain function from here. So this is contained here. So I can just take injection from here to there. But then I take the quotient. So I just take a function here, and I take to its class. Okay, Z plus LB. So this is linear. Oh, this is linear, and since this guy is contained here, okay, this is linear. This is all we need actually. And now we are going to compute the kernel, and we are going to show the kernel is just LA. And then we are done. If the kernel is LA, then my isomorphism theorem for groups, we have that the quotient is isomorphic to the image over there. Yep. So who is the kernel of phi? So this is just the function living here. Yeah, such that you want the class will be 0, so you want that Z has to be also here. So this is just this space intersects on this space. So our claim is that when you intersect this and this, all you get is LA. Look, this inclusion we have already. LA is contained here, LA is contained here because A is smaller than B. So we just need to do the other direction. Okay, so we take zeta here. Then we have that. Then we have two things. Divisor of zeta, by definition, is larger than this, and larger than this. Okay. So we just add B here, so we have that. Now is we do a small trick. So the divisor of this plus B, I would just add B in both sides. Okay, so this has to be larger than plus, and I put the A over there. Has to be larger than B minus A, and this is positive. And if you do the same here, now I will add B plus E. So, sorry, I'll add just E here. So Z plus B plus E is larger than E, and E was larger than 0. So you have that this divisor is larger than this positive divisor. This divisor is also larger of this positive divisor, and they have nothing in common. Because by hypothesis, we asked that the support of this and this are empty. So the only way to this happens is that actually this guy has to be larger than this plus this one, because they have no place in common, this both. But what this means? This means now you can just cancel P and P, E and E. So you have that this is larger than minus A, and this means that, yeah, it was here. Okay. So we know the kernel is just what we wanted. Okay. So when I quotient by the kernel, I have something injective over there. So let's just keep this here. And now I will go on to prove what I wanted for pure gaps. Oh, we have this. For proposition, we want to say when a pair is a pure gap. So we can just check this. We are going to prove that this is not. Okay? This is our definition. We are going to prove that we can just check that one. Okay, so for now, I'll just do something like this lemma. So you consider this. I'll just write like L of AP plus P minus 1Q. And I'll put down here A minus 1, P plus P minus 1Q. And here we just put AP plus PQ. So you see, well, this guy is certainly smaller than this guy. And well, how do I go from here to there? I have to add P. So here we put the same thing. And now, well, you can think that this is divisor A, this is divisor B. So when you do B minus A, what do you have? You have just Q. And what you have done to get this one, you have added P. So we have B minus A equal to this, and we have E equal to P, as in the lemma we just proved, okay? And so, yeah, this is a positive divisor. This is also a positive divisor, so we can apply the lemma. So I know that this function here is injective, okay? So if it's injective function, we know that the dimension here has to be smaller than the dimension here. So we have that L of AP plus B minus 1Q minus this dimension has to be smaller minus this one. And well, I want to see this So now I want to prove, let's say, I want to prove this in the proposition. So if I have like this equality, I want to show that equality. So I just put things in the right side. So we have to put this and this together. Okay. So if I look to this, I have that. I'm proving this. Okay. So I have that L of this plus PQ. No. Okay. No. It's not this one. Oh. Okay. No problem. No, I will not do that. I'll do something else. So to prove this part, what I'm going to do is look like this. We have that, well, this L of A minus 1P we just need to see things in the right way. So this one minus this one is smaller than this one. Yeah, just put this to the other side. So this minus this is larger than, and I put that one here. Okay. And what I'm saying, I'm considering that AB is a pure gap. So we know that this dimension here is equal to this dimension here. So by hypothesis, I have this is 0. If this is 0, this is 0. P mais PQ minus this one. So this is 0, so this is 0. So okay, so this is 0. And then what we have? Then the guy we wanted, okay, then what we have is that this guy, yes, okay, it's here. Huh? So since this is 0, we have this is equal to L of A minus 1P plus BQ. So because this is 0, and this is equal by hypothesis again. So use again to L of AP plus BQ. And it's done. And well, if you want to prove the other part, if these dimensions are, if this dimension is equal to this, you just need to look at this in another way. Oh? So, well, it's similar. Huh? Now you have to look to the difference of this guy and no, and this guy, but then I have just 10 adding. So okay. So to the other side. So we have these dimensions equal. So it's actually it's easier. Similarly, so we have now these dimensions equal. This is equal. Then you look to this one. Now you just have that this, right? So this divisor is always smaller than this divisor. And this divisor is always smaller than this divisor. Okay? So you don't need that for this part. So you have this dimension equal to this dimension. So actually this dimension has to be equal to this and it has to be equal to this. Okay, and you just do the same thing if you let P here and A minus 1 here. So yeah, so this proposition characterizes perfectly pure gaps at these 2 points. Okay? So we have this. Well, so we have a characterization of pure gaps in terms of dimensions of a Riemann-Roch spaces, but yeah, but computing dimension of a Riemann-Roch space can be a difficult task. So we'll show that if I am in a Kummer extension for 2 totally ramified places, I have a way to do that. Okay, so this is what we are going to show now. So we go back. So I'll just keep this composition here, and we go back for Kummer extensions. So we have again a Kummer extension. So F equal to F cubed X and Y over F cubed of X. We just have Y to the M equal to Fx separable. They are coprimes, R and M. So this gives us only one point at infinity in the curve. Okay. And so we are going to fix, and again, we fix, as we just did before, we fix Q infinity and the Q1. Who was Q index 1? Okay, Q1 is just over P1, that is the place associated to X minus alpha 1. Okay, it could be any of the roots. There is only one. And so what we know is, we know that by the proposition, we know that a pair is a pure gap. So if and only if, we have the characterization. If this dimension is equal to this dimension. So to find pure gaps, actually what we need is to be able to compute dimensions of Riemann-Roch spaces. So now we are going to have help from a very nice theorem from Maharaj. So this is so before I state the theorem, I need a definition. So we'll do like this. So if you have any divisor in F, okay, so Suppose D is the sum. So here, any place Q, if intersect with the rational function field, you have a place here. So this place is over some place. Okay, so we are going to define what is the restriction of this divisor. So we say that the restriction of data, this is a definition. So what do? You do the sum for P in the rational function field, and now you put Q over P. Okay, so you are going to do a sum for P. What are you going to sum? You sum the minimum. So what you do is you divide the number NQ by all the ramification index of the places. Okay, you have Q, so you have here, but maybe another Q here. Let's say this was over the same place. So what you do is you do this of the ramifications of Q over P. Okay, and so maybe this is not an integer. So what I do, I take the floor. So it's the minimum of the floor for all the places over P. And P. So you take a place P down here in FQ of X. You look up. If no one appears here, it means that NQ is 0. So this is 0. You have nothing here. Okay. But if you take a place P here and you have a place appearing here, how do you do to do the restriction? Well, this is the law. Okay. So this is it. And now it happens that, well, there is a condition on this divisor. Like, so this is important. If, this is a very important if. Oh, if the is fixed by the automorphism group as this, then, so, well, this sounds, what is this fixed by the automorphism group? Well, we are not going in details now, but it happens that if in your divisor D you only have totally ramified places in your extension, so this divisor is good. It satisfies this condition, okay? So in particular, and Q is totally ramified. What does it mean to be totally ramified? Well, for us here, if you are in Kummer extensions, it's a degree M extension, so you want that ramification index is M. Okay, so ramification is total. So, and our divisor D is going to be this guy. So for this guy, AQ infinity plus BQ1, since they are both totally ramified, I'll be able to apply the theorem. So the theorem says, if D satisfies this property, we have something very nice. Then we know that the Riemann-Roch space by D in F, this is just the direct summon from T equal to 0 to R minus 1. sorry, to m minus 1 of, you take t plus. So we are in a Kummer extension, okay? So Kummer, we have this y to the m equal to fx. Okay, so d plus the divisor of y to the t, but not this. This divisor is up there. So just take it restriction here. Okay, so it will be just the sum of these dimensions. So it will be, okay, so it will be this times y to the t. So, so what are you doing? You have a Riemann space up here. You want to compute the dimension. So what this theorem tells you is that, well, this Riemann space, if the divisor D behaves well, has this property, we can just break this vector space as the direct summand of m vector spaces down here in the rational function field. And well, in the rational function field, it's easy to compute dimensions. Okay, because if I have this, what is the dimension of L of D? Okay, so from this, what we have? Well, you have that L of D is just the sum, because this is direct sum equal to 0 to m minus 1. I know to compute, I have the divisor of y, I have my divisor this, so I know to compute this, I know to do the restriction. So this is just the sum from here of the dimension of this guy. Oh, yeah, what is good is that this is a divisor here. And now we just remember, recall that in the rational function field, it has zeros. So if degree of A is larger than 0, look, 0 is larger than 2g minus 2, because this is just minus 2, because is 0. Then we can apply Riemann-Roch theorem to get the dimension. Okay? Then L of A, the dimension is just the degree of A plus 1. So it means that, well, you know to compute the dimension of these guys, if you know that. Okay? And, well, this is the Maharaj's theorem is this one. So if we apply this theorem for this divisor, okay, so I will not do all the computations, but I will give you what we get in the end. So take Kummer again. Right? So for this guy, we can apply this. We do all the computations, and we get this, that AB is here. Okay. So the condition will be if and only if every t from 0. So no, if and only if every t here satisfies one of these conditions. So one condition is that A minus RT. So who is R? R is the degree of F over M plus B plus T over M. This number is negative or this number is positive. And in the case that it's positive, we need something else. Huh? So we need this is positive, and the condition is that M does not divide B plus T. M does not divide this guy, and M does not divide this guy. Okay, so I give you a number, AB. Okay, and well, M and I are given by your function field extension, so you have to do these computations. You check if this is smaller than 0 is okay. If this is larger or equal than 0, then you need this condition. So for sure, this is not going to be satisfied for every A and B. Okay, so we know how to find certain pure gaps in a Kummer extension. So tomorrow, what we'll do is we are going to show how we can improve the minimal distance of codes using pure gaps, and then we are going to work out an example over the Hermitian function field for these places, Q infinite and Q1. Okay. So now what I'm going to do, I'll do a brief introduction on codes, and then we go to differential algebraic geometry codes, and then we are going to show how to use pure gaps to do that. So well, a linear code is a vector subspace of SQ to the n. Is a FQ. Okay, so well, it's simple. Any vector subspace you take here, it's a code. But well, you need to create your codes in a clever way, in such a way that it's hard to find out who is your code you are working on when you do cryptography. So what we are going to do here, we are going to use algebraic curves later to define these codes. So a code is this. We say that the length of the code is the size of the ambient where it lives. So the length. N is called the length of the code. Oh, now it's length. So we have out the dimension that we call K. is the dimension of C over FQ. So attached to a code, we have length and dimension. And we have something else. Huh? So we say that, if C is in C, we say C is a code word. And, we want to measure how far away code words are from each other. Okay? So we are going to do the Hamming distances. So what is the Hamming distance? If I give you C1 and C2 in C, so C is in FQ to the n, so these guys are vectors. So I say that the distance between C1 and C2 is just the number of coordinates where they differ. They are different. Okay? And this is called the Hamming distance. Yeah, Hamming introduced this distance. And it's really it's a distance, it satisfies the triangular inequality. Okay? It satisfies all you need, like in a metric space. So this is a distance. And for any code word, we also define omega of C1, that this is going to be the distance of the code word to 0. Okay, so this is just the number of coordinates that are not 0. C1I is not 0. This is called the weight of your code word. And what is the minimum distance of our code? Is the minimum distance between all code words C1 and C2 in the code that are non-zeros. Okay, and we can show that this is also the minimum of the weights of all your code words. If you just look to the distance of all code words to 0. So the minimum distance so is D is just the minimum of the weight of C for C in C and not 0. So you have we are over finite fields, so your code, like it's a number of finite numbers of vectors. Okay, so this distance tells you, how far away the words are from each other. And this can help you to correct the errors. Okay? So the minimum distance is like you look at to all these guys. For example, for this code, the minimum distance should be this. If these are all vectors in FQ to the n. Yeah? So this one. Okay. And usually we use the notation that C is a NKD code. So you are given the parameters length, dimension and minimum distance of the code. Okay, usually we use like this. And so like if you want to correct errors in a code, you'd like to have a large minimum distance because yeah, if your words are far away from each other, or you have like something like this. So, for example, you send a word, and the word, you have some bits wrong. So instead of getting this vector, you get a vector here. So you see, if you just measure now the distance of this vector, you see that it's not in the code, yeah, because there is no code word with distance 0, so it's not there. But now you can check what is the distance between this vector and this code word, and between this vector and this one. Well, this is the smaller one. So how I correct this wrong vector I received? I have to correct this vector by this code word because this is the closer to it. So this is the idea. So larger is your minimum distance, more errors you can correct. Okay. This is with the family of error correcting codes. So you'd say, well, I want D really large, but yeah, but you cannot have D as large as you want because these parameters they're connected. So we are just going to prove a really simple relation between them. Okay. So there are, well, many relations between them. So for example, let C be an NKD code. Anyone? Okay. So you consider you have D, you consider this set. So you have A1. So this and this. So here you have a vector of size n. So all these are 0 and these are elements in Q. So yeah, this is a subvector space of FQ to the n. Okay, so this is a code. And what's the dimension? Well, the dimension is D minus 1. So dimension of this code is D minus 1. And if you have a code word here, what's the weight of C? Well, C has at most D minus 1 values, not 0. So the weight, what was the weight? Well, the weight is the number of non-zero coordinates. So the weight of this code has to be less or equal than D minus 1. Okay? But you see, but if I have a code word on C, since the minimum distance is this, we have that the weight of any code word on C has to be larger or equal than D. So these things both together tells you that this code and this code have nothing in common. Okay? Well, so if I just do this code, C has dimension K. So K plus D minus 1. This is just the dimension of C plus dimension of AD. Okay. Well, and since they have no intersection, this is just the dimension of C plus AD. And yeah, this has to be a subvector space of FQ to the n. So this is smaller than n. So if we look to all this together, what we get is K plus D has to be smaller than n plus 1. And this is known as the singleton bound for codes. So if you add dimension plus minimum distance, this is at most n plus 1. Okay. And so now we are going to construct some codes over function fields. So we are going to do a code over FQ to the n, use an algebraic curve or a function field. Why this code will be nice? Well, these codes are good because they give you the code they present. It gives a lower bound on the minimum distance, just based on the curve, on the genus of the curve. So, okay. And tomorrow we'll do the theorem of pure gaps to improve codes. So we just call them, AG codes. These are, so we need something before we make the definition. Okay. So take a place P in your function field. Okay. And NT, a prime element at P. Yeah, so what does it mean? Yeah, it means that the evaluation VPT is what? So now, if you look at to any function, we have already used this. Any function Z in your function field, okay, we can expand it. We can write it as the sum for E equal to N to infinity to AI Ti for N in Z. So yeah, because if N is negative, you have poles at P. That's the idea. Okay? So locally, you have your function can be written as a power series. Okay? So we have this, and I'd like just to recall that I didn't say till now, but actually working with function fields, you are working with Riemann surfaces. So this is exactly what you do when you are doing Riemann surfaces. You have this, you have a function. Locally, you can expand in your power series, okay? And then we have what we call the residual of P of the function Z. Yeah, but the residual of the function at P depends on the prime element you have fixed. So this is just going to be A minus 1. This is by definition. Yeah? A minus 1. If I give you a differential, so omega will be, we call like this, all the differentials. So what are differentials? Well, we are at this place, so we can just think that they are of the shape z dt. Okay. So if you have a function field like this, so we are taking a prime element at P, but you could take any, we call a separating variable of the function field, can be used also to write this. Okay, because, well, we need to believe that this behaves well. If I change the place, the definition is well defined. Okay, so this. So this and T, well, I'll put like this. I think it's better. Yeah, it's better. And X is a it's a variable. What does it mean? That's a separating variable. It means that when you have your function field, S. What is a separating variable? Every time you do FQ of it, this has dimension finite. This is a separating variable. You don't have just one. You have many you could use. So you fix any one. Okay? So you can think your space of differentials like this. Okay? And now you know how to add differentials. You know how to do everything. And so your differential omega is just z dx. And we define the residual at P of the differential omega. This will be just the residual of P of the function z. Okay? Yeah, so you have to take your function z and write as a power series. So you have your place P. What do? You take the function z, you write as a power series here in a prime element at P, and then you look to a minus 1, this is the guy. So we have this. And we also know that the divisor, we are going to define the divisor of the differential. So we also say that VP computed at W is just, by definition, is VP at Z. And the divisor of the differential is the sum for all the places. VP of W, P. Okay? And well, the divisor of the differentials is always a canonical divisor. So do you remember we didn't know, well, we needed a canonical divisor to compute the dimension of him or her spaces. Well, guess what? If you take the divisor of a differential, you have a canonical divisor. Okay? So now we are ready to define the code we want to work on. So our code will be like this, huh? So so we fix P1, P2, Pn, okay, and pairwise different rational places. In a function field. And well, we let now D to be the sum of these guys. So you consider the divisor D, that is just the sum of these rational places. And now you choose G, a divisor such that Pi is not in the support of G. Or any I. So what is now we are ready to define the code. So the code, okay, let's just do this first. Now we define this space, so of G minus D. So this is a space of differentials such that the divisor of the differential is larger than this. Okay, so is the FK space of differentials in F of such that, okay, all the difference is 0 or this is larger than G minus D. And now we can define the differential code C omega using D, using G. Okay. So what you do is you compute the residual at P1 of omega and the residual at Pn of the differential omega for which omegas? For omega living here. So okay, and well, this is contained. Yeah, you have P1, Pn, FQ to the n, and since your differential lives here, this is well defined. Okay, so this is going to be what are you are computing the residual, and okay, so we have this, and we can prove. So we know something about the minimum distance of this code, and we know that the minimum distance of this code is always larger than degree of G minus 2G minus 2, where G, as usual, is the genus of your function field. Okay, so this is what we call the classical lower bound for these codes. So what is really nice about these codes is that, well, you already know something about the minimum distance. So what you want to do is, well, can you improve this minimum distance? Can you give something like larger than this? So what we are going to show tomorrow is that, yeah, you can use pure gaps, and you're going to prove that we can improve this minimum distance for codes in 2 points. Actually, we are doing everything 2 points, but it could be done in n points. Okay. So yeah, so tomorrow we start with this theorem that improves this minimum distance for differential codes. And well, today we are finished a little bit earlier, and that's it.